Hello, my name is Robert Smith, and I'm with New River Community College. And today we are looking at the process of electrolysis in a qualitative fashion. In both my qualitative and quantitative analysis of electrolysis videos, we will be dealing with the electrolysis of water. And this is not the only reaction that you can conduct electrolysis with, but electrolysis is essentially applying a potential to a cell, the two half reactions in a cell, to make it go in a non-spontaneous direction, to push for a non-spontaneous reaction by applying a potential. So what does that mean? Well, typically if you have two waters, they're liquid, you can perform, you can lyse or break up. Electrolysis is breaking up through electricity. You end up with two hydrogen gas and one oxygen gas. And that's something that you learned quite a long time ago. But really, this can be broken up into two half reactions. The first of which is one that we've dealt with before, and we're going to write it in the reduction form. So 2 protons plus 2 electrons yields a 1 hydrogen gas. Okay, and the other form that we have is again going to be written in the reducing form, is O2 plus 4H plus 4 electrons yields 2 H2O. So now you're starting to see how this is familiar. And if we were to try to match, let's call this equation 1, equation 2, and equation 3. If we were trying to match equation 2 and 3 to equation 1, we would flip equation 3 to the other direction. So let's do that. So 2H2O yields O2 plus 4H plus 4 electrons. And we get this from the equations 2 and 3 from our standard reduction potential table. And then we can compare this new equation with equation 2 and note that there are 4 electrons here, but only 2 here. So we need to multiply equation 2 by 2. So now we end up with 4H plus 4 electrons yields 2H2. And when we add these together, the 4 protons on the left-hand side cancels with the 4 protons on the right-hand side. The 4 electrons on the left-hand side cancel with the 4 electrons on the right-hand side. And we end up with 2H2O yields O2 plus 2H2, which is equation 1. So that's how you would look at these half reactions. Now, if we look at equation 2 and equation 3 again, let's call this 3 star. So we want to look at equation 2. The cell potential for this is 0. It is the standard by which we observe all other cell potentials. 3 star is actually 0.40 volts. So if we look at these and think about this for a second, in the past, with galvanic cells, you have had the species with the higher, more positive potential would be the species that is the cathode, that would reduce. And the species that with the lower potential would be the anode, and it would oxidize. But instead, we've got it the other way around. Our cathode is number 2. So our cathode, at the cathode, you have 4H plus 4 electrons minus or yielding 2 hydrogens. And at the anode, you actually have your 2 H2Os yield O2 plus 4 protons plus 4 electrons. So it's very different just based on which species is occurring at the cathode, which reaction is occurring at the cathode, and which reaction is occurring at the anode. It's the opposite of what you would expect for a regular spontaneous reaction. So that shows this to be non-spontaneous. And in fact, if you do cathode minus anode, so for this, we would have is equal to 0 volts minus 0.4 volts. So this would be negative 0.40 volts. And then if we compare that to our changing Gibbs free energy, we would have negative 4 times our Faraday constant, which I don't need to write out, times negative 0.40 volts. So even like, the Faraday constant is positive and pretty much 96,500 in its reduced form. So this negative 4 times negative 0.4 is going to give us negative 1.60 volts. I'm sorry, it's going to give us positive 1.60 volts. And we know that a change in Gibbs free energy that's positive is non-spontaneous, whereas a change in Gibbs free energy that is negative is spontaneous. So in this electrolysis process, what is happening is you are applying a potential to a cell to promote it to react in a non-spontaneous reaction to occur. And that's used often in industry for such things as electroplating and so forth. So in our next video, we'll be looking at something akin to electroplating, but we're going to just look at electrolysis in a quantitative fashion.